This meeting is being recorded.
Okay, so back after the glitch. Sorry about that. But I wanted to show. Opened again. Okay. So back after the technical issue, and we are back. And I wanted to show, just to say that this truth table was explaining that this was already the definition of what it means of taking a Majorana word of this binary summation of indices, because it gives us again a binary index 0, 1, and here 2L. So it's a binary string of length 2L, which is fine to use this definition. And this is already solving the problem for us, because we were asking when is this identity, and the answer is that this is m mu times m nu. So basically what we get is that trace of m mu m nu is -1, and I will call it phi, -1 phi of mu and nu, and then delta mu nu. Okay, because we will be having the trace of mu plus nu, and this has to be the zero binary string. And this is the important bit. I will put it more in red, which means that those traces are giving us sign flips. So if I have the trace of two operators x and y, then this is the summation over mu, and I will have x mu, y nu, and then this factor -1 phase factor mu nu. So that's something that we need to get. And the point is that Grassmann integration can do this phase factor for us as well. That's something that where we want to arrive. I'm not sure if I will be able to finish the whole thing today, but basically, if you read the paper which doesn't have this computation, you will see that this is basically the point. So the point is that when we are in Hilbert space, Majorana words are traceless. So we just computed now what happens when we multiply them together. When we multiply them together, we get this phase factor, and it will be ±1. And basically, this phi function.
What's delta mu nu?
Yeah, it will be this sum here. Okay, so let me write this. And this phase function, it's not, yeah, it's a little bit like a phase function. This one is appearing all the time when we do multiplications, and when we will go to the generalized Wick's theorem. So here I need to sum k prime from 1 until 2L with the constraint that k is smaller than k prime. And what I will be doing is I will have mu k times nu k prime, which is exactly the exponent here. Yeah, we just define this function.
And what's the delta?
Delta, this is the Kronecker delta here.
Right.
And
so
basically
it's 0 unless mu and nu are identical.
Yeah, they need to be equal. Yeah. Thanks for yeah.
Okay, so in that case, it seems like, in a way, the phase factor is something that's completely determined by one of the, like either mu or by nu, right?
In this case, it's simpler, but sometimes you can have a more general product.
I see. Yeah, here,
So, for
because we're
example,
taking the trace, it becomes like this.
yeah, the trace collapses a lot of things here.
I see.
But if we will be taking free operators, so you can generalize this consideration to x, y, z, then there will be many ways of creating an identity, right?
Got it. Thanks.
And then those reshufflings will be much more complicated. So we already defined this phase function here. Sorry, maybe it shouldn't have been in red. But it's just more general, and it's good to have that one already in. Okay. All right. So, okay, now we are back on full screen. Sorry, boss. Okay. So now we computed this in Hilbert space. And the point is that Grassmann integration can compute it for you using Grassmann integration. So now we would like to compute the equivalent formula, and I will probably mess up the sign, but it will at least explain to you why this stuff works. P of nu, and then the Bravyi kernel here, PT G. So this is a computation that we need to do, and this should be basically equivalent up to some signs that we need to check to trace mu m nu. So that should implement that for us, and everything is linear. So I can put here x mu and then y nu. So I will get this also here, x mu y nu. And then, of course, I can sum it over mu and nu, and I can sum it over mu and nu here as well. So the question is here whether the exponential here is implementing for us a little bit something like a Kronecker delta, right? Because Varun was asking about this, and basically in some way this is the correct expression for maybe something that implements the delta in the right way, right? But on this side, it's clear that I wrote the double integration g p of the symbols of x because they are linear, so we can expand in the basis y, and then just the Bravyi trace kernel. Okay, so this is clear by linearity. And if I'm summing this, then it's clear that this is trace of x and y. So now my point is that we would like to do this individual computation. P, maybe I'm doing it in this order. And we do it for the individual words. And if we prove it for the words by linearity, it will work. EPT, G. Okay, and the computation is a little bit messy and complicated, but we can check whether this will work. But basically, that's the essence of the computation, and I'm now not sure if I have this in mind correctly, but let's see. Okay, the first thing we would like to do is to reshuffle the integrations. To do the integration like this. To L and G1 P1, and the phase factor for this, if I'm not mistaken, I didn't prepare this for today, unfortunately, but I think this is -1 to the power to L, which would mean that this is actually +1, or it's -1 to L. But I don't remember exactly right now. Sorry about this. But anyway, we can now reshuffle those two, and that will give us -1. It's exactly the same reshuffling that we did. So it will give me I write 5 because we are in the general case. And what I have is G1 to power mu1. And now after the reshuffling, I have P1 to power mu1. And the exponential is commuting with everything else. So I can write 1 plus P1 G1. Okay, and now I see already that this will work. I think we were looking at this a lot with Alex, because this is enforcing that they are the same. First P1, P2L, and then G2L. Okay, so what I did here was to expand E to PTG to realize that actually it cancels after the first order. So it's actually a multilinear function here in the Grassmann generators. And here the order of the product doesn't matter because we are it's even, so it's commuting with every other Grassmann number. Plus P2L, G2L. So now I took those products and I reshuffled them to bring them closer to the individual indices. Yeah, it's still non-commutative, so I'm not writing the product sign. But you see that this depends only on the first Grassmann number. Sorry.
Yeah, I think there is like a dragging that's going on, and that's making the browser go to the previous page.
Yeah, I don't know why, because maybe I switch off the mouse. And the pen is on the side. It's the first time I'm using the bot, so. Okay. So, but we are almost there. We will now see the most important computation, and then I just recap and we are done. So now I was doing this integral here on the bottom. And I said I want to reshuffle. And that's something that I don't want to compute here because I will confuse myself. But this is ±1 to reshuffle the integrals between each other. And the point is that now I can make them block by block because I additionally have this phase factor that allowed me to bring those two together. And the exponential is quadratic, so it's even, so I can commute it through for free. So now the only thing that I need to do to wrap up is to look at the individual parts. So let's look at the individual parts. G1, P1, and then G1 to power mu1, and P1 to nu1, and then 1 plus P1 G1. So the first to have indices, the second to don't have indices. So this is G1 P1, and then G1 mu1 P1 mu1 plus the double integral again. Okay, against G1, against P1, G1 mu1 P1 nu1, just repeating it. But for sure I have P1 G1. And if we inspect this, the integration forces mu1 to be equals to nu1 to be equals to 1. Or here the integrand, so to speak, is forcing those two to be 0, because if they appear there, they drop the whole monomial. So it's mu1 is equals to nu1 is equals to 0. And so what we arrive at is that this is delta mu1 comma nu1. And if I wouldn't confuse myself with the sign, I would get that basically the integral of g, and here against p, g mu, p nu, then the Bravyi trace kernel is actually doing the trace for us, because what we get is -1 phi mu nu, and then delta mu and nu, because then it happens for every entry in the product. So we have here all the way until 2L, right? Okay. So basically, this finishes the computation. Basically, what this kernel here implemented was to select on those many dimensional binary indices. It gave us the delta, but because it's Grassmann integration, it also computed correctly the phase factor. Huh. Well, we can finish the recording here. So we're doing relatively well on time today. Maybe I will just summarize and we can finish in this moment, I think. Okay. So so I was talking about using the idea of integral operators. So for example, what is the delta operator? And actually with this operator, I think I had it somehow wrong in mind, that this was supposed to be the delta, but this was doing something else as an integral operator here. So I will need to think about what it does. But it was just an example. You can take any function, so to speak, of your g and p Grassmann numbers, and you can get some kernel for an integral operator. And that will be an integral operator between the subalgebra generated by the g Grassmann numbers to Grassmann numbers p, because we are integrating against g, which will remove them completely. So this is something that Grassmann integrals share with functional integrals. Okay, and then I went to the more serious example, the one that we wanted to study, where we said, well, what happens if I take an exponential function of the scalar product here, which just means we exponentiate this bilinear here in P and G. And the point was that we wanted to implement the trace by this very nice compact formula. And to do this, we needed to understand that if we define this dictionary by Bravyi on the words and then have a linear expansion, then we need to also do what we did last week, showing that the Majorana operators are an orthonormal operator basis on the space C to 2 to power L. Okay, that was just an example that this can compute, for example, the fidelity for us. And now what we were saying here is that we can just do this orthonormal expansion of those two operators. And then we can talk about computing the trace of those two operators, which means that we will need to multiply m mu and m nu together and ask when is this identity, because if it's not the identity, then we get a nice 0 in the trace, because it will be a traceless operator. So here it was a messy computation. This is looking ugly, but when I was probably talking, it was easier. And in the end, we just needed to reshuffle, and we got that the product of those two is again a Majorana word. It's always a Majorana word, and a XOR addition modulo 2 is telling us the binary string for which this is the Majorana word, but we still have this kind of plus minus sign. And this plus minus sign we were computing in detail. And we got this function here, which will be appearing later on as well. And whoops. Oh, no, I messed it up. No. Okay, zooming through again. Sorry about those glitches. Okay. So this function will appear again, and I think what I was trying to say before it dropped off is that this might be playing a similar role as a symplectic scalar product. It doesn't want me to say that. Okay, not like this. So we're almost there. So whether it's a scalar product or not doesn't matter, because we get this formula here. That's the trace of those two operators is summing up the coefficients, but you need to understand when they cancel into the identity in the trace. All right. And then we were computing what happens when we consider the Grassmann side of it. And the expansion here, by definition, of those symbols is the summation mu and nu with coefficients. And then you need to just understand what happens to the individual words for any mu and nu. And that will give us the full integral here of the Bravyi formula. And we wanted to relate it to the trace here, which we knew that has kind of those flip signs. And yeah, and then I started computing this stuff here. So we compute against P and G because we are taking the trace, so nothing is left. We have mu and nu left and the kernel here, which means that we will start integrating. And here I needed to reshuffle the integrals. So reshuffle integrals. Okay. And that will give me some phase factor, but that's basically related to the parity. I think usually it was. And then we were doing the other reshufflings, and that was the non-trivial reshuffling. And as soon as we had that, we had an integral here, and we got that this integral was indeed a delta. That was this detailed computation here for G1 and P1. So I have them here. And basically, this is forcing me to have them in. And this is forcing me to not have them in. But either way, they are equal. Either way, those two indices have to be equal, which means that this is a Kronecker delta of those two numbers. Okay, so once we do it for all the entries in the product, we get the multi-index Kronecker delta here. But from reshuffling the G mu and P mu nu words, we got this phase factor here. And that phase factor also appeared for the operators, which is basically bringing us to the end of the proof. There's a couple of steps missing, but it's explaining how you get to the formula that Bravyi wrote in his paper. Okay, I stop here.